Students, good morning. I think right now only 18 members are there. I will in the last class we will discuss about the first class things. I start. Already I have started the fourth model. The fourth model, gate level design. Okay, the basic things in the half of the model, that basic circuit concept. In that we'll go in detail of the sheet resistance. I think in the last class I discussed about the sheet resistance, and gate capacitance, wiring capacitance, fan in, fan out, choice of layer. These are the topics in fourth model, half unit. Okay. What is meant by basic circuit concept? What are things are there? What we have to go for the basic circuit concept? Basically, in VLSI design, wiring up nothing but is an interconnection, connecting from the one terminal, one point to the another point. Wiring up of a circuit takes place through the various conductive layer, which are produced by the mass processing. So it is necessary to know that resistive and capacitive characteristics of each layer. Okay, why we have to study only these two things, that is resistive and capacitive characteristics? Because the thing is called delay. Tau equal to RC. Tau equal to delay is purely, it is based on the two parameters. One is called resistive, second is called the capacitive. For that reason, we'll go in detail about resistive characteristics and capacitive characteristics of each layer. Concepts such as resistance RS. RS is the sheet resistance. And standard units of capacitance, square Cg. Square Cg is standard unit of capacitance, square Cg, which helps in evaluating the effect of wiring and input-output capacitance. Okay, from that we can evaluate the effect of wiring and input-output capacitance. All these things are purely based on the two parameters. One is called length, second is called the width. All these things are taken into account. The sheet resistance and capacitance are derived purely based two parameter. One is called length and width. If they are same, length equal to width, then we can call as a square Cg. When L equal to W, length equal to width, then we can call it as a square. Okay. The delay associated with wiring with inverter and with other circuitry evaluated in terms of delay unit tau. Delay associated with wiring with inverter and other circuitry are evaluated in terms of the delay unit tau. Tau equal to RC. Okay, first we'll go for a sheet resistance RS. Sheet resistance is the RS. The sheet resistance, is measure of resistance of thin film that have uniform thickness. We'll go to measure a resistance of a thin film that have a uniform thickness. Consider a uniform slab of conducting material of resistivity rho. Here resistivity rho of width W, width equal to that sheet width equal to W, and sheet thickness equal to T, and length between opposite faces A and B is the L. L is the length of the sheet, W is the width of the sheet, T is the thickness of the sheet, rho is the conductivity of the sheet. From this we will find that what is a derivation for the sheet resistance. Resistance of a square slab of a material. When we say that square, it should be length equal to width. Length equal to width. For a resistance is derived as conductivity rho into L divided by area. This area is nothing but as T into W, thickness into width. When we consider that, let's consider L equal to W for a square CZ, square slab, then sheet resistance. That resistance equal to, resistance is nothing but rho divided by T. This we call as that square will call as sheet resistance. That sheet resistance is expressed in ohms per square. Resistance is measured in ohm. Sheet resistance is measured in ohms per square. Sheet resistance is measured in ohms per square. Okay, here the entire thing resistance A equal to Z. Z is nothing but L divided by W. This sheet resistance equal to nothing but rho divided by tau. Rho divided by tau is nothing but sheet resistance. Rho divided by tau equal to sheet resistance. Okay. When we sheet that resistance of a material is Z into RS. Z is the length divided by width. Z is the L by W. Z is the L by W. Just why I am stressing this, because we are going to take for the calculation purpose, we will take this thing L by W. Okay, consider that consider a resistance resistance AB between a two opposite faces, where A is the area of the cross section. Consider in the case of L equal to W, it means that square resistivity material, where RS is the ohms per square or sheet resistance. Hence the resistance of mass layer depending on the thickness and resistivity of the material of the layer. Okay, the resistivity is purely based on these two parameters. One is conductivity and the thickness. Okay, the resistance concept applied to the mass transistor and inverter. Consider a transistor structure by distribution a equally dimension region for a channel, and simple NMOS transistor has the length equal to 2 lambda and width equal to 2 lambda. For a simple N-type pass transistor, NMOS transistor has the length equal to L equal to 2 lambda and width equal to 2 lambda. For that the resistance R equal to R can be this for a simple transistor. Already we have gone through the design rules. In the design rules, minimum width of the diffusion and minimum length and width for the diffusion and polysilicon is 2 lambda. Length also 2 lambda and width also 2 lambda. Okay, already we have gone through these things. P diffusion, N diffusion, all the diffusion should be minimum spacing of 2 lambda. For a transistor, for an NMOS transistor, length equal to 2 lambda and width also 2 lambda. Length of the diffusion and width of the diffusion as well as polysilicon width and polysilicon length should be 2 lambda. Okay? 2 lambda is the width of the diffusion and length of the polysilicon. That is 2 lambda. Just simply it is a 2 lambda by 2 lambda. Length and width are same for a square CZ. Here Z into RS. R is equal to resistance. Total resistance R equal to, already we have gone that things called R equal to Z into RS. Okay, Z is 2 lambda divided by 2 lambda. 2 lambda divided by 2 lambda, which is equal to, which is 1 square that is 1 square into RS is the rho divided by T. Rho divided by T. This is a value, standard value for a uniform slab, which is equal to rho divided by 10, rho divided by T, which is equal to 10 to the power of 4 for an NMOS device. For an NMOS transistor, this value is 10 to the power of 4. Okay, for the examination point of view, this sheet will be given. The constant values are going to be given, that conductivity, NMOS, PMOS, polysilicon, and what is the metal. These values they will give. Only we have to calculate that based on what the length and width are given. Okay, if you know that, it is easy. Okay, here just say, in this case, when this transistor is length equal to width, then the resistance value is 10 to the power of 4. If they have increased the length of the device to the 8 lambda, width of the device to 2 lambda, okay, then the square Z value equal to 8 lambda divided by 4 lambda, which is equal to 8 by 4, which is equal to 4. 4 into 10 to the power of 4. 4 into 10 to the power of 4. Okay, here, hence the length to width ratio denotes the impedance Z and is equal to the 1:1. In this case, 1:1 ratio. Consider the another transistor has a channel length equal to 8 lambda and channel width equal to 2 lambda. Thus, Z equal to L by W. L is the 8 lambda, W equal to 2 lambda, which is equal to 4. Okay, for that, resistance R equal to Z into RS. RS is sheet resistance. Sheet resistance is fixed, 10 to the power of 4 for an NMOS. Okay, 4 into 10 to the power of 4. 4 into 10 to the power of 4. That is 4 square into 10 to the power of 4. 10 to the power of 4 ohms per square. Square get cancelled. That is 10 to the power of 4. 4 into 10 to the power of 4 ohms. When length equal to 8 lambda and width equal to 2 lambda. Why we have derived? We will see that. These two things are required. One is called for an 1:1 ratio. 1:1 ratio when it is 1:4 ratio. This we have increased 4 times. For this, the increased value is 4. In the ZPU by ZPD, already we have derived the things called ZPU to the ZPD. One inverter driven by the another inverter. The ratio is 4:1. In that we are going to use this one, 4:1. That 4 value is 40k. 4 into 10 to the power of 4. That is generally we can write this can be written as a 40 kilo ohms. We can straightforward. We can write it as a 40 kilo ohms. Okay. For this, we can write it as a 10 kilo ohms. We can write 10 to the power of 4. We can write it as a 10 kilo ohms. On resistor, both if you sum these two, that is 10k plus 40k, it is total is 50k. Okay, we see that thing. Okay, it is in the just when the length and width are same, then it is 10 to the power of 4. If you increase the 4 times, automatically resistance also increases. Then these are the standard values. They already I have told that there are total 3 different technologies. One is called 5 micrometer. That 5 in the 5 micrometer. That length and width are in terms of the 5 micrometers. Okay. In that, if you use a metal, a standard value is 0.03. For a diffusion 15 into 15 to the 100 that value silicide is 2 to 4, polysilicon 15 to 100, N channel, already I have told that I have taken, we have took this value 10 to power 4 when we have took a 5 micrometer technology. The value is 10 to power 4 for a N channel. For a N channel, the resistance value is in terms of sheet resistance value in terms of the RS ohms per square. The value is, if you take a N channel, it is 10 to power 4. If you take a P channel, why it is greater? Because it is slower. That is, P is slower than the N channel. For that reason, 2.5 times slower than the N type. For that sheet resistance also same thing. It is 2.5 times. The sheet resistance value is more than that of the N channel. N channel is 10 to power 4. P channel is 2.5 into 10 to power 4. Similarly, if the technology it is 5 micrometer, orbit is 2 micrometers. Orbit is 2 micrometers. In this case, 0.04, 0 to 45, silicide not be applicable. Polysilicon is 15 to 30, 2 into 10 to power 4, 4.5 into 10 to, just observe that values. If you increase here length and width are decreases, or within the 5 micrometers, 5 into 5, that is 25 micrometer square is the area. In this case, area is decreases, but sheet resistance value is increased in the N channel and P channel. In the N channel, it is 2 into 10 to the power 4, 4.5 into 10 to the power 4. As the area decreases, sheet resistance increases. As we decrease the area, sheet resistance is increases. Already we know that the formula is inversely proportional. Sheet resistance is inversely, as we this it is increased, it is decreased. If you increase this, it should be decreased. If you decrease this, it increases. If area is decreases, it also increases. That technology, if you 2 micrometers, from 5 micrometer to 2 micrometer, 5 micrometer is area is large, in the 2 micrometer area is small. If area is small, resistance value increases. That is that the formula that R resistance value equal to, resistance is rho into L divided by area. Area is nothing but as that, area is W into, okay, that is the values are, okay. These are the, for the orbit 1.2 micrometers, it is orbit is 2 micrometer, next is 1.2 micrometer. These are the 3 technologies for a designing. Okay, next we'll go for a sheet resistance for an inverter. Sheet resistance for an inverter. Just say the why we have took a length equal to 8 lambda and width equal to 2 lambda, Z equal to L by 2 equal to 4. Already we have derived that thing. A sheet resistance R equal to R into RS. RS is for an NMOS. It is an NMOS inverter. NMOS inverter, one is depletion mode, another is enhancement mode. It is in a first transistor, it is in a depletion mode transistor. Second transistor is pull up and pull down. Pull up to pull down is 4:1. 4:2, that is depletion is 40K, enhancement is 10K. Okay, 4:1. 4 is pull up, 1 is pull down. It is 4 times. It is 1 time. It is 4 times. It is 1 time. Length to width is 4 times. It is 8 lambda divided by 2 lambda. You have to take as length equal to 8 lambda, width equal to 2 lambda to equalize the both the 2 transistors operation. To make operation of 2 transistors equally, you have to maintain that this transistor is 4:1, that 4 times greater than the pull down device. This is 4:1. 4:1 to make a 4:1, you have to take that L equal to 8 lambda and width equal to 2 lambda. That is L by W equal to 4. Okay, sheet resistance equal to R equal to Z into RS. R already we know the Z, that is 4, and sheet resistance of the NMOS is 10 to the power 4. Here we have these are the standard values. 10 to the power 4, which is equal to 10 kilo ohms. Similarly, hence ZPU to ZPD equal to 4:1. ZPU to ZPD is 4:1. Hence, the on resistance between VDD and VSS is the total resistance, total series resistance. We have connected in series. That is on resistance of the on resistance of the pull up device, on resistance of the pull down. That is On resistance of the depletion mode is what? And on resistance of the enhancement mode transistor. Depletion mode transistor and enhancement, that is on resistance. On resistance of depletion mode is 40K. On resistance of the enhancement mode is 10K. Total resistance is 50K. Total resistance is 50K. It is a calculation for an inverter. In one exam, they asked about this question. Calculate a total resistance of an inverter, of an n-mass inverter, Okay. Next is area capacitance of the layer. Next, capacitance C equal to epsilon inverse epsilon naught A divided by D. A is an area, D is a thickness. Okay. Epsilon naught is the permittivity of the free space, that is 8.854 into the power of minus 12 farads per meter. Okay. Permittivity of free space is 8.854 into the power of minus 12 farads per meter, and epsilon inverse is the relative permittivity of the insulator, that is silicon dioxide, which is equal to 4. Okay, these two are constant, that is epsilon naught and epsilon inverse are constant. Varying terms are the A and D, area and the thickness. Okay, these are the standard values, typical standard values for the three different technologies. Okay, the values are measured. The capacitor is measured in farads. Capacitance is measured in farads. Okay, in general here they have given values in terms of the picofarads into 10 to the power of 4 per micrometer square. Picofarads into 10 to the power of minus 4 divided by micrometer square. That is, in the bracket, whatever the value, they are the relative values in the bracket. In this bracket, whatever the things are there, they are the relative values for that thing. For example, say gate to channel value is measured in picofarads into the power of minus 4% per micrometer square is 4. Relative value is 1. Relative value is 1 in 5 micrometer. Similarly, 8 micrometer 8 and 1.2 micrometer is 16. Diffusion is 1, 1.75, 3.5 like that. They have value. Polysilicon 0.4, 0.6, 0.6. For metal to substrate 0.3. Relative value is 0.075. Okay, we will go for one example. Then we will come to know that what these values, how to substitute these values for the calculating a sheet resistance. Look, for calculating a capacitance square Cz. Okay, standard unit for a capacitance will go to measure in terms of the square Cz. Standard unit of a capacitance, that is square Cz. It is defined as the gate to channel capacitance of a mass transistor having L equal to W. L equal to W, standard square as shown in the above figure. The unit is denoted by square Cz. The unit is square indicates length and width are equal. Square indicate length and width are equal. May be calculated for any mass process as follows. Simply, if you take a area per standard square. If you take a area for in a 5 micrometer technology, that is length and width are same, 5 micrometer. Length into width is area equal to 25 micrometers. I want to convert into capacitance value. The standard square value is 10 to the power of 4 minus 4 into picofarad per micrometer square. This is a standard value. Already we know that this is a standard value from the gate capacitance value in this diagram. Here see, a gate to channel value is 4 into 10 to the power of minus 4 divided by micrometer square for a 5 micrometer technology. 5 micrometer technology की The value is 4 into 10 to the power of minus 4 per micrometer. Okay, that is a standard value. Capacitance value is this one. I want to convert into the standard value. Standard is in terms of the square CZ. Square area into area is 25 micrometer square into 4 into 10 to the power of minus 4 picofarads per micrometer square. We have converted these values in terms of the per micrometer square. Okay, that micrometer get cancelled, micrometer square get cancelled. 25 into 4, it is 100 into 10 to the power of minus 4, which is equal to 0.01 picofarads. Capacitance value is 0.01 picofarads for a 5 micrometer mass circuit. Similarly, if you take the 2 micrometers, that is area is 2 micrometers into 2 micrometers, which is equal to 4 micrometer square. The capacitance value, standard values for that is 8 into 10 to the power of minus 4 picofarads per micrometer square. The standard value square CZ equal to 4 micrometer square into 8 into 10 to the power of minus 4 picofarad per micrometer, which is equal to 0.01 picofarads. Just say that even you have decreased the length to width, L equal to 2 micrometer and width equal to 2 micrometers in the 2 micrometer technology. Okay, this is a standard value. Standard value, capacitance standard value is 8 into 10 to the power of minus 4 into area, which is equal to square CZ value. From this square CZ value as well as the sheet resistance value, that resistance value, if you multiply that, you will get a delay. If you multiply these two things, you will get a delay. Okay, for 1.2 micrometers mass circuit, which is equal to 1 point into 1.4, that is 12 into 12, that is 144, which is equal to 1.44 micrometer. The capacitance value is for the 1.2 micrometer is 16 10 to the power of 4, which is equal to 1.4 into micrometer into 16 10 to the power of minus 4 picofarad, which is equal to 0.0223 picofarads. Okay, these are the three how to calculate the values for a different technology, different process. Okay, in the next class we will go for the calculation of the capacitance value for the different layers. We will go for one problem. This is an important problem. The one exam they asked about this problem. We will derive these things next class. So ivi rendu cheptam. Calculation of a capacitance and one problem related to the same problem as in the textbook itself, Paknal textbook. Okay, if you have any doubts, any queries, you can ask.